In this section, we'll be talking about limits and continuity. So the very first thing we should start by doing is just talking about the concept of a limit. Now, I like to give you a very informal definition of it, and just something to always keep in mind. What is a limit? Well, a limit is a y value. Now, when I use y value, please remember y is the output variable, the dependent variable. So it's the value, it's the not the input but the output, if that makes sense. So it's the y value that your graph, function, etc. It could be, any representation. I'll put graph in quotations to kind of remind you. It doesn't have to literally be a graph. It could be a graph, it could be a function, it could be a word problem, it could be whatever version of it you want, but it's the y value that your graph, now here's the key word, approaches. Okay, it doesn't actually have to reach this value, it just has to approach it. All right, now let's talk about notation. Then I'm going to give you 1,000 examples of these so you can see what I mean by approaching a graph, approaching a value, but not actually having to reach it. All right, now notation. Let me start you off with the very cryptic, very theoretical notation, and then I'll give you some examples, and I hope it'll all kind of help out. So what we're going to say is it's going to look something like this. It would look something like this, where you have the, excuse me, the limit. Okay, so what we read is we read the limit as x approaches some value. Okay, in this case they were using c to represent any value. Okay, so what we have said so far is we have the limit as x approaches c of our function f of x. So what we're saying is, okay, our graph, our equation f of x, we want to know the y value, because remember, that's what limit really means. Limit really means y value. So what we're saying is I want to know the y value that my function f of x reaches or approaches as my x values approach c. Okay, and the answer to that, and however we wrote it, is L. All right, let's give you something with all these letters. Okay, so what we're going to do here for a quick little just notation example would look something like this, and we'll read it, and I'll sketch out a visual that may or may not actually be correct, but who really cares? There we go. Okay, so what we're going to say here is say the limit of our function as x approaches 2 is 4. Or another way of reading it is saying the limit as x approaches 2 of f of x is 4. So what we're saying is I have some crazy graph where I have the x value of 2, and what we're saying is here at the x value of 2, the y value of my graph is going to be approaching the value of 4. Whoops. Come back, axes. There we go. Okay, and what we're going to do is we're going to say that that's 4 right there. Okay, so what we're saying is as we approach from the right hand side, excuse me, that's the left hand side. Let's try that again. As we approach from the left hand side and as we approach from the right hand side, my y values both are approaching the value of 4. All right, let's do some examples and do this over and over and over and over. All right, so here we go. Now I've given you a kind of nice graph, and much nicer one than my crew drawing. And let's do this first limit together. Okay, so the first limit I'm going to look at here is problem number 1 right here, just highlighted in yellow. And what we're going to say is, let's read it. What it's saying is the limit as x approaches 0 of f of x is what? Okay, so what we need to do is find where our x values are 0. Well, that's the same on every graph. It's right here at the axes, right? Right there would be 0. So what we're going to say is, what y values does my graph approach as our graph for our graph as our x's approach 0? So what y value are we going towards? So as I come from the left hand side, you can see it looks like the y value of my graph, the output value of my graph, looks like it's approaching the value of 1. And then as I approach from the right hand side, again, it looks like my y values are approaching 1. So I think we can all agree whether or not the graph actually equals 1 at the x value 0 is completely irrelevant. We don't care if f of 0 actually equals 1. Don't care. All we care about is what are they approaching? Is it getting close to the values of 1? And I'd say yes. So therefore, our limit is 1. Now, in some problems, we don't care if it approaches the same value from the left and from the right. We only care about one direction. So that's what you're going to see in this next problem. This next problem, you'll notice, is the limit as x approaches 1, but there's this little positive sign. And you'll notice the next problem has a little negative there too. So what that is telling you is direction. It's saying we don't care about what y value our graph approaches from both left and from the right. We only care about one side. So what we're going to say here, or how I remember it, is I think about my axes. The right hand side, when you're going to the right, that's the positive numbers, and when you're on the left hand side, that's the negative numbers. So when you see a positive, when you see a little positive here, what that's saying to you is you're on the positive side. So as I come from the positives and as I approach my x value, what y value am I going towards? So when I come from the positive numbers and go towards my value of 1, what am I going towards? AKA, that is always going to be from the right hand side of your x value. So we're looking at the x value 1, numbers from the right. Well, it looks like the y values are approaching 4. I hope that makes sense. If it did, great. Pause the video. Try the next problem on your own. Try problem number 3. See if you can get that answer. Okay, so now hopefully you've unpaused the video. Let's go ahead and I'll do it with you. So because it's a negative sign, that means where are your negatives? Negatives are on the left. So as you come from the left, hand side of your point, what y value does our graph seem to be approaching? Well, it seems to be approaching the value of 2. So therefore it has a limit of 2. Now you'll notice neither of these points actually have closed circles at 1. Neither of these lines, neither of these graphs have closed circles at 1. They are both, if you were to substitute in the value 1, you wouldn't get out 2 or 4. You would actually get out 3 because that's where the closed circle is. But notice these both have limits. They're both saying we still have a limit. They're both fine because we're only talking about one side. Now, and remember, limits only talk about approaching. Limits only talk about what number are you getting close to. They don't care what number you actually reach when you're there. So now for the last problem. What does it mean if this problem doesn't have a little plus or a little minus above the 1? It's just the limit as x approaches 1. So what are you going to do? Well, we have to think about what does that mean? Well, with the problem number 1, when we said approaching 0, we didn't have a plus or a minus, so that meant from the left and from the right. So in this case, when there's nothing there, you have to say, okay, what y value am I approaching from the left and from the right? And that's the problems we just did, and we saw one of them approached 4, the other one approached 2. So therefore what we say is, since they don't reach the same number, we say it doesn't exist. There is no limit for this function at the x value of 1. There could be limits elsewhere, but just not at x as x approaches 1. All right, let's do more. All right, now this problem, let's start off by focusing on, for this function shown, decide the x value or values for which the limit does not exist. So we have to remember what makes it so a limit does not exist. We just got done with that. Well, it's where it approaches from the left and approaches from the right to the same x value, but the y values go to different places. So if you think you've got it, pause the video, give it a try. Okay, hopefully you unpause the video, and let's talk about that. So as you kind of scan with your pencil, what we're looking for is a place where the y values don't meet up. Whenever you have a break or a jump or something in your graph, and one side goes to one place, coming from the other side goes to another place. So 1 looks okay, but 2, as I come from the left-hand side, you'll see it looks like we're going to the y value of 2, but when I come from the right-hand side, it looks like we're going to the value of 3. So therefore, we would have a limit that does not exist at x equals 2. And that's the only place I see on this graph where that is the case. I think x equals 2 is it. Now, could we do more limits if we wanted to? Absolutely. So let's, for a little bit of extra practice, let's do this. If you want, let's talk about the limit as x approaches 4, because this one is usually one that will trick people who are a little iffy. So if you think you've got it, give it a shot. If you don't think you have it, just keep watching. Okay, hopefully you unpause the video at this point if you were one of the ones who wanted to try it yourself. Here we go. So what we're going to do is look at the value of x equals 4. What we're going to do is look at that x value and say, all right, as we approach on the left, what y value does it look like we're approaching? Well, to me it looks like we're approaching 2. Now as I approach from the right, what y value are we approaching? Well, the value of 2. So therefore, does this have a limit? Absolutely. Why does this freak students out sometimes when you take your test? Well, because it's just an open circle. It's not even defined. If I asked you to say, if you plug in 4, what do you get out? You'd have to say, I don't know, it does not exist. It's not defined because there's nothing there. Well, even though it's not defined at the value of 4, actually I'm going to say not defined, not does not exist. Not defined. I hope I spelled that right. All right, so even though there's no x value, when you plug in 4, we have no idea what y would be. There can still be a limit as you approach from one side. You're approaching 2. As you approach from the other side, you're approaching the y value of 2. So therefore, the limit is 2. Okay. Now, that's with graphs. We've now found a whole bunch of limits with graphs. Now let's do it with some functions. Now, could we theoretically graph every single one of these and find the limits? Absolutely. And on some very complex functions, that's what we will do. We would just graph them and look at them. But let's see if we can find some shortcuts here. Now, I think we can all agree the function x squared minus 3x plus 2, we all know it's a quadratic of some kind. We may not know exactly where it's graphed, but I don't know, maybe it looks something like this. And we all know it's opening up because it has a positive leading coefficient. So what we're going to do is, who knows where the x3 is? We'll figure that out. But I think we can all agree that there's no jumps, breaks, or any kind of strange corners or anything in this graph where we might have a limit that does not exist, because we all know it's a parabola and we know how they're drawn. So couldn't we just take the value of 3 and substitute it into here and just say, okay, well, 3 squared, excuse me, not plus, 3 squared minus 3 times 3 plus 2, well, what does that equal? That would be 9 minus 9 plus 2, so therefore I just got 2. Does it make sense to say, all right, when I plug in 3, I get out 2, so therefore the limit of this function would equal 2? Well, absolutely, because we know there's no breaks, no discontinuity. Well, we don't know what continuity is. That comes later. But there's no breaks, jumps, or weird things going on in the graph because it's just a parabola. So therefore, if we know when we plug in 3, we get out 2, then if I were to approach from the right and approach from the left, they would both approach the value of 2. So the first method we have for finding the limit of a function is the plug it in rule. You just take whatever your limit is, whatever your x value is for your limit, substitute it in. And if you know that there's no breaks, jumps, graphs, or anything weird going on in that graph, then you can just take that value, substitute it in, see what value it gives you, and you're great. There you go. All right. Now, this one's a little more interesting. Now, if you remember from either your pre-calculus class or your college algebra class, we graphed a whole bunch of rational functions like this. So, so that might come into play. But let's first just try the plug it in. Let's just try substituting in a number and seeing if it works. So this would be 3 squared minus 4 times 3 plus 3 divided by 3 minus 3. Uh-oh. I don't really care what happened in the numerator because notice what happened in the denominator. Dividing by 0. That's undefined. We know that there's either a vertical asymptote there or a hole there. So, back from MAT212, right? Or from college algebra or brief calculus. Or pre-calculus. There we go. So, let's see what we have there. If this numerator factors, if you don't remember, here's your brief reminder. Let's factor the numerator, and if that divides with the denominator, then we'd have a hole. If it doesn't divide, then we're going to have a vertical asymptote. So let's factor that numerator. I think it factors out to be x minus 3 and x minus 1, all divided by x minus 3. That's awesome, because those divide, which means we are left with the limit as x approaches 3 of x minus 1. So now, what we know about that point, if you were to graph this thing at the value of x equaling 3, we don't have a vertical asymptote. That's not what this graph looks like. This graph, it's going to look like the graph of x minus 1, which is just a diagonal line. That's super easy to draw. But at that value of x equaling 3, we had a hole. So what does that mean about our limits? Well, graphically from the other graphs we did, we know as we approach from the left and as we approach from the right, our y values are going to approach the same number. Just when we substitute in 3, we'd get undefined, but who cares? Limits don't care. So now with our simplified function, we are able to actually just substitute in 3. 3 minus 1 equals 2. So what we know is as you approach from the left and as you approach from the right, we're going to get the y value of 2. Yes, there's a hole there, but that doesn't matter to limits. All right, so next method for finding limits here. Method number 1 was to plug it in. Just plug it in. If it goes, great. Okay. Method 2, we have some kind of issue. We have a hole. We have a vertical asymptote. We got something funky going on. Well, let's figure out what it is by using a little bit of algebra, simplifying. And good news, it was a hole. So we can now just go to the plug it in rule. All right. On to C. Now this one. Notice this one's only asking with the plus sign. So stop and ask yourself, what does that mean? Well, plus, that's the axes. Okay, that's the plus side. The plus is on the right. So coming from the right. Okay, so what we're going to do is think about this graph where it's only asking us what y value are we approaching as we come towards the x value of 3 from the right-hand side. I'm going to use something called big little logic to get me through this problem, but there's lots of ways of doing it. You could sketch the graph. You could we can't algebraically simplify this, but I think you'll see the big little logic is kind of fun. Now, as we approach 3 from the right hand side, let's think about what kind of numbers that would be. So the x value of 3, if I'm coming from the right hand side, that would be numbers very, very close to 3 but slightly bigger because they're on the right. So maybe 3.00001 or something like that. So if I were to substitute in a value like that, what would we see? 3.0001 plus 4 divided by 3.0001 minus 3. Well, 3.0001 plus 4, that's, I don't know, that's about 7, right? That's pretty close to 7. Divided by, what's 3.0001 minus 3? Well, that's 0.0001. And if you were to do that in your calculator, you would see that that is about, what, I don't know, it's going to be pretty big, right? Tens, hundreds, thousands, 10,000, I think it's going to be that, 70,000. Holy cow, that got really big. Now, if we kept getting even closer and closer to 3, so instead of doing 3.0001, let's do 3.0000000001 plus 4 divided by, do you guys see where I'm going with this? Okay, we just got super close. So therefore I'm going to be, again, about 7 in the numerator, but now my denominator I'm going to have 0.000000, however many zeros I drew before. So now what just happened to my number? If I divide by this, instead of getting 70,000, I'm going to get something even bigger because, well, you can check it in your calculator if you want, but this is tens, hundreds, thousands, 10,000, 100,000s, millions, 10 millions, 100 millions, billions, 10 billions. Okay, so we're going to have to get 10 billions here. So that's, there we go, 1 millionths, thousands. Woo! All right. So it seems to me the closer we get to 3, the bigger our number is going to get. Well, instead of doing all this little math, couldn't we just written something that looked like this? 7 divided by something really, really little is going to make something really, really big. Well, in math, what's big? Well, that's infinity. So therefore, the limit to this as we approach from the right-hand side is going to end up being infinity, because the closer we get to 3 from the right-hand side, the closer to infinity we get. Let's verify that in the calculator. Let's take a look. All right, so let's go ahead and turn our calculators on, go into y equals, let's clear everything out. All right, so don't forget parentheses around your numerator and your denominator. So I'm going to do x plus 4 divided by x minus 3. And I'll just do a standard window, so I'm going to go zoom 6. And we should see there we go. That's exactly what I wanted to see. As you can see, as we come towards the x value of 3 from the, whoops, pardon me, I didn't get it down far enough here. Let's move it over to the side. Didn't want that popping through. All right, let's try that again. As we get to the x value of 3, that's right here, as we approach from the right-hand side, we can see our graph going up towards infinity. So there we go. That verifies, graphically we have verified what we just figured out using a little bit of logic. So that's part C. Now on to part D. How can we get through this? Well, let's try big little logic again. Let's go big little. Instead of worrying about a vertical asymptote and say, are we going up or are we going down? Now we're working towards the limit as x approaches infinity. Well, if you remember, that's just a horizontal asymptote. What is our graph doing? I know it's a different graph, but here, in a rational function, what is our graph doing as x goes on forever? Now, if you remember from college algebra how you get a horizontal asymptote, we can use that to find this, or we can use big little logic, and we can say, all right, I can't plug in infinity, that's breaking the rules. Infinity plus 4 is considered bad form, but instead what we can say is it's some really big number plus 4 divided some other really big number minus 3. And that's basically, if you stop and think about it, like if you had a billion, million, trillion, quadrillion, I don't know, making up some crazy number, plus 4, if you just won the lottery and then someone said to you, I'm going to give you $4, do you really care? Not really. So that's essentially big divided by. Now, same idea. You just won the lottery and someone says, but I have to take away $3 in taxes. You're like, oh, fine, take it. I don't care. I still have a really big number. So what is big divided by big? Well, that's about 1. So therefore, this limit is going to be 1. So there you go. I wanted to give you those techniques. Those are your really 3 techniques for finding limits when they give you a function. Technique number 1, just as a recap, is plug it in. If you know there's no jumps, breaks, graphs, anything, it breaks in your graph, anything kind of funky, just plug it in. Number 2, if you can algebraically simplify, because that means you have a hole in your graph and you can find your limit once you simplify and you just plug in, substitute in your numbers. The third technique is big little logic, saying if I'm going to be dividing by something really little, well, anything divided by something little makes something big. Right there. Anything divided by something little makes something big. And then you can always have bigs divided by bigs, which makes 1, and just kind of think about what you're looking at. So maybe if you ended up with a problem that had big divided by 2 after you did all of that, well, something big divided by something 2 is still something big. So therefore your answer would be infinity. So just a little bit of logic there will get you through those types of problems. Okay, so moving on. One last method I want you to be able to do. We've now found limits using algebra and a little bit of logic. We've done limits looking at graphs. Now let's do a table of values. Okay, what does it mean what does it mean? What am I asking you for when I ask you for a limit? Well, it's the y value as x approaches. Right? So here, when we're doing x approaching 1, that means from the left or from the right. What does it mean? Oh, from both sides. So we're going to need 2 tables. So if you think about it, as we're approaching 1, from the left, what kind of values would you be seeing there that are slightly less than 1? Well, and to be able to talk about what's happening, we need to kind of make a pattern or a visual for us to kind of see what's happening as it occurs. So as we're getting closer and closer to 1, we might be seeing something that looks like this, right? Point 0.9 would be a little further away, a little far away, then 0.99 would be getting closer and closer, 0.999 would be closer, and we'd be getting closer and closer to 1. So now what I want you to do is, can you fill in the x values for the other half of the table? Pause the video, see if you can figure out what those would be. We want to have values that start a little further away and they get closer and closer and closer and closer. Okay, so pause the video, give it a shot. All right, here we go. So again, starting 1/10 away, I might start at 1.1 and then saying, okay, something that would be closer to 1 than that would be maybe 1.01, then 1.001, then 1.0001, so on and so forth. So now, to be able to talk about what the y values are doing, I need to actually substitute all these numbers into the function. Well, I don't want to do that by hand. Out comes the handy dandy calculator. So let's go ahead and type in our new function here. Don't forget your parentheses. So that would be what? X squared minus 1 divided by the quantity of x minus 1. Okay. Now, once you have that in, we're going to have to go ahead and type in all these values into that. And I like to do it in the table because it'll just spit it out for me in a nice way. So I'm going to press second, go up here to table graph. There we go. Now this calculator, again, if your calculator is already this way from the last class, then good for you. You don't have to change anything. I'm going to have to go back into table set and change it from my independent variable from auto to ask. There we go. So now when I go in here, I've got values. Now, actually though, I should say, if you have this left over from the last class, you might notice that there's some numbers in there. You don't have a blank screen. So how do you get rid of them? Well, you can actually just type right over them, or you can use the delete button. If you press the delete button, it just gets rid of them. Okay, so I'm going to start with that first part of the table. I'm going to start with my, I can't get the decimal points of 0.9. All right, I apologize. Type in 0.9. Still off the screen. There we go. All right. So when I type in 0.9, I get 1.9. Then when I type in 0.99, I get 1.99, and so on and so forth. And we can kind of, I think we can develop a pattern here. I think we can kind of see what's happening. 1.99, 1.999. So I think we can pretty much safely say, I believe as we get closer and closer to the x value of 1, it looks like our y values are going to get closer and closer to the value of 2. Now, for this limit to exist, we need to approach the same thing from the other side as well. So go ahead and type in your values of 1.1. Whoops, excuse me, don't do it on there. Let's try that again. Yeah, no, not right there. Try it in the calculator. Okay. 1.1, 1.01, 1.001, and you'll see that these values all seem to be approaching 2.1, 2.01, 2.001. So it looks to me like as our x values get closer and closer to the value of 1, it looks to me like our y values get closer and closer to the value of 2. So therefore, I'm going to go ahead and call it and say it looks to me like the limit of this function as x approaches 1 of whatever this function was up above is equal to 2. Okay, so I just want to show you another representation. We can find limits using tables of values. So if they don't give you the function, they might just give you tables of values and say, what do you see? What does it look like? And you can make the decision there. You can do it from graphs. You can do it from equations. All right. Now, let's get to our next concept, continuity. We spent all that time on limits. Good news, continuity is very short, very quick, very easy. The easiest way I like to put continuity, the way I like to say it, is if you can draw the graph without picking up your pencil, then it's continuous, which is what the idea of continuity is. Are there any holes or breaks in your graph that make it so you're undefined as you travel along? If that is the case, then it is not continuous. If you can draw a graph without picking up your pencil, it is continuous. And please, no smart Alex who say, oh, I can draw a circle without picking up my pencil. No, that's a hole. That doesn't count. Okay, so no smart Alex in the room today. All right, so definition of continuity. Now, the formal definition says a function is continuous at x equals some value if and only if the limit of that function is equal to the function at that value. So what we're saying here is, if we had some function where we said, okay, here's where x equals 4, I don't know, the limit as x approaches 4 of whatever that function is should equal the same number as just plugging in the value of 4. So if that were the case where I had a hole there and it was removed, then this would not be true, because when I plug in 4, I get out one number up here, and when I use my limits left and right, I get out some other number down below. Does that make sense? Hope it makes sense. Ask me if you need any more clarification. So the idea is, even though a graph, you look at this graph, it is clearly not continuous. There are several places that this thing just not continuous. But even if it's not continuous, there are still, what we can do is talk about intervals over which it is continuous, because if you're doing something with it, you may not really care about the places where it's not continuous. You just care about where it is. Excuse me. So where is this graph continuous? Now, I'm going to say this graph starts at 0 and goes to, okay, where's our first jump break? Somewhere that's not good. Well, that looks like the number 1. So, and then it's not continuous there. So then our next place of continuity would go from 1 to 2. And then after that, we have a jump, so we're no longer continuous. And we're going to go from 2 to 4. And last but not least, we're going to go from 4 to, I don't know, let's call that 5. 4 to 5. Okay. So just want to kind of put that in your mind, that even if a graph is discontinuous at one point, it doesn't mean that the whole thing is shot. We can't talk about limits or whatever, or later on derivatives. It's okay, just as long as the thing you're trying to do doesn't either use the discontinuity or it doesn't care about the discontinuity, like a limit from one side opposed to a limit from both sides. Okay. And there are 3 rules to continuity. These are the 3 things you can check for. Note, they are rule number 1, rule number 2, rule number 3. There are no names to these rules, which means I will not test you on them. I will ask you to use them. So for example, in a problem, I might give you these written out as they are and say which rule does this graph break, or which rule does this graph not follow. So that way you just say rule number 1, rule number 2. You don't need to memorize them. Okay, but you need to be able to read them and understand them. So the 3 rules of continuity. The first rule, rule number 1, f of a is defined. If your graph is not defined at some value a, because there's a hole there, it can't be continuous because there's a hole. It has to be defined. Okay. Rule number 2, the limit as you approach a must exist, meaning they both must approach the same value. If they don't approach the same number, then they can't be continuous. And last but not least, the value, again, this is what we talked about before, the limit as you approach from the left and from the right must equal the same value as if you were just to plug it in, substitute in the value a. There's your 3 rules. Okay, I hope those make sense. They make sure you just can kind of read them and know what they mean so they don't throw you on a test. All right, so what did we talk about in this lesson? What were our 3 big objectives? Let's make sure we got them all. Okay, so the first objective was, can you define a limit? Do you know the just kind of informal definition of a limit? What is it? Ask yourself. Pause the video. Okay, what was the informal definition of a limit? It's a y value that your graph approaches. And remember, it's a y value. Okay. Part number 2, objective number 2. Can you find a limit? Can you actually, if I give you a graph, if I give you a function, if I give you a table of values, think of all the different ways that I could kind of represent information and say, can you find it? Do you know how to find it? Do you know all the techniques? And objective number 3 is, do you understand, if I start talking about continuity, do you know what we mean? What continuity means? And are you able to verify its three rules, its three requirements. And remember, I am not going to ask you to memorize the three rules. Just have to be able to look at them and understand what they mean and say this one is true, this one is not. Okay. Fantastic. Get started on the homework. It was a pleasure having you in class.